In this video, we'll be discussing one of the major parts of a transformer model called positional encoding. So if you've ever wondered why the authors of Attention is All You Need chose a combination of sinusoidal curves for the positional encoding vector, we'll try to build that intuition from scratch. We'll be using basic mathematics and not going into 3D space or complex numbers or a complex plane. Though this topic has been covered elsewhere, I've tried to break down the intuition behind these concepts to the point till we reach the final equations as proposed by the authors. So I'm assuming you have a basic idea of how transformers and attention in transformers work. If you don't, I'll give you a very high level overview, or you could also check out this amazing video on attention by 3 Blue 1 Brown. Right. So the first step, what we do is we break down the input sentence into tokens or tokenize it. So for simplicity, we'll instead of tokenizing words, we'll assume each word is one token. So I'm going to take I as one token, am as one token, and so on. Each of these tokens has a vector associated with them. So how attention works is that we look at the vectors of our neighborhood words, not neighborhood, actually the whole sequence that we give, and we try to change these vectors based on by paying attention to our neighborhood words. So for example, the vector for going, let's say it has values like 0.2, minus 0.3, and so on. These will be changed by paying attention to these other vectors. Right, so transformers, unlike other sequence processing models like RNNs or LSTMs, do not process data in order. This means they need a way to incorporate the order of the input data or positional information, if you want to call it. And that's where positional encoding comes in. So each of these words will have a positional vector or a positional encoding also associated with them. Without positional encoding, a transformer won't be able to tell the difference between two different sequences of the same set of words but in different orders. If I take a sequence A and I jumble up the words and give it to the transformer, it won't be able to do that, but we want it to do that. So positional encoding helps the model understand where each word is in a sequence. So we'll use this particular sentence, I am going to play football this evening, to understand this concept better throughout this video. So let's get started. What is the, like, let's take the most naive approach for positional vectors. So let's call them PIs. Let's take just a sequence of numbers, positions through 0 to 7. Let's say 0, 1, 2, 3, 4, 5, 6, and 7. Let's assume that these numbers are the positional vectors of these tokens. So using simple numbers like we have just done right now might seem direct, but this method can be misleading for the model because it treats these positions as numerical values, which could imply an unintended order of importance or magnitude. Let's say we have a 510, it will give more importance to the 510th position, right? So this could lead to biases in how the model interprets the sequence and could also lead to exploding gradients. So now we know what problems we have, what is the obvious next step. We could say, okay, to prevent exploding gradients, let's normalize this. So let's just divide these by 7. So now what we have is we have the positional vectors that are going from 0 to 1. We have solved one problem and introduced another. This variability can be problematic. Why? Because uh, let's say we have two sequences. One has 50 tokens and the other one has 100 tokens. A positional encoding value of say 0.3 represents the 15th token here. And the same 0.3 will represent something like a 30th token over here. Right. And ideally we want a method that maintains consistent positional relationships regardless of the sequence length. If we give input of let's say 500 tokens, we want it to work for input sequence of 1,000 tokens while testing, right? We don't want to limit our model on the sequence length of the input token in the training data that we have, right? So we know that normalization will also not work. What could be the obvious next step? Let's use binary representations of uh, the numerical values that we have. So here we have 0, 1, 2, 3. So binary values 0, 1, 2, 3. This method seems clever, right? Because it uses fewer dimensions to encode the positions as compared to the naive numerical approach. However, it introduces another issue, discontinuity. How? Let's look at the first four. Let's just look at 0, 1, 2, 3 to limit it to two dimensions, right? So for 0, we have 0, 0. For 1, we have 0, 1. For 2, we have 1, 0. And for 3, we have 1, 1. Okay, so let's assume that this is the embedding dimension 1 and this is embedding dimension 2. And let's try to plot this on a graph to see if it's discontinuous or not. Dimension 1 and this is embedding dimension 2. If we plot a graph with these two dimensions, embedding dimension 1 and 2, have 0, 1, 0 and 1. A 0 will come over here, 1 will come over here, 2 will come over here, and 3 will come over here. This is 0, this represents 1, this represents 2, this represents 3. If we want to draw a curve between these two, this is how the curve looks like. Let's try to analyze this graph a little further. The major problem with this graph is that this is discontinuous. And as you can see, if you move from this position to this position, you flip both the bits from 0, 1, you go to 1 and 0. So two major challenges that we see in this graph. The first one is that what we want our model to do is that small changes in position, we want this to be reflected as a small change in the representation. And that is not happening. The binary method leads to large jumps in encoding for adjacent positions, and this can confuse the model as it tries to interpret these as meaningful patterns. The second issue that we have with this model is that it is not continuous. Continuity in positional encoding helps the model to generalize better to positions that it hasn't seen before. A continuous encoding scheme would mean that the positions are numerically close. The positions that are numerically close would receive similar representations, and this would aid the model in understanding patterns that span across multiple positions. And the lack of smooth transitions could also mean that the model's ability to interpolate and extract useful positional information is also limited. So what should be the next step? We suppose we want a continuous curve and we want unique representations for each value. Unique representations we also had in the binary approach, but as we saw that there are other drawbacks of this approach. Right. So what should be our next obvious step? We need a continuous curve and we need unique positions to have unique values. So the first thing that comes to mind is a sine curve. Let's say we have the sine curve. Let's say we have about 50 samples in our training set. So P1 will be here, P2 will come over here, and let's say while testing we have 70 tokens. So where will these go? We'll see that these values will start to repeat, and P50, a training set had 50 tokens, so P51 will be the same as P1 and P52 would be the same as P2. So now this means that we are back to not having unique values for each position. And that is something we understood that we need. So to address this, what can we do? Uh, One thing that comes to mind is, okay, let's create another dimension where each dimension is a sine curve, and let's change the frequency. So just stay with me for a bit. We'll try to understand how this works. Uh, so let's say we introduced a different frequency sine curve. So what will happen with this is that each position will have a P1 and a P1 dash, right? So each positional vector will be a two-dimensional space. So the positional vector for P1 will look something like the first dimension would be point P1 and the second dimension would be point P1 dash, right? So each dimension is a sinusoid curve, is a sine curve, and we have encoded each point in two dimensions. So this way we have unique representations for all points. This additional dimension effectively creates a more complex positional landscape. Similar to what we saw in binary, there were two dimensions, right? So here also we have introduced one extra dimension. So if you know what the actual equation given by the authors of attention is all you need is, you know that there is a cos instead of a sine. So before we get into that, before we get to why we used a cos and where did that come from, let's look at a couple of intuitive analogies to understand this particular graph of multiple frequencies. So let's say you have um, three volume knobs where the first volume knob increases the volume by 1 decibel, this increases by 2, and this increases by 4. So with just three knobs, you can encode a value from 0 to 7, right? So with just three of them, just how binary numbers work, right? So each frequency adjustment, we can look at it as like turning a knob, allowing us to encode positions in a multi-dimensional space, and thus effectively expanding the range of positional signatures we can create. So this is the first analogy. Another analogy, how we can think about this is that two people speaking the same words but at different frequencies. So while the content of their speech is exactly the same, they're speaking the same words, there is a unique characteristic or a tone to each voice. So similarly, in positional encoding, while the content might repeat due to the periodic nature of a single sine wave, adding another sine wave at a different frequency changes the pitch of the encoding, right? And thus we get a distinct voice. We can understand it like this way. So now, if we look at what our positional encoding matrix that we have understood till now is, it looks something like this. I am going to play, right? And for I, we have a sine wave at a frequency omega naught. Then we have a sine wave at frequency omega 1, and so on. Similarly, we have a sine wave at omega naught, a sine wave at omega 1, and so on, right? This is how our current positional encoding matrix looks like. So now we're going to talk about uh, why we need a linear transformation in this positional encoding matrix. So one thing that uh, we want to have, one functionality we want this to have is that if we want a positional encoding of a small delta x from x, we need to be able to calculate that by a function. So here, this we calculate by this transformation function. So this should be a linear transformation. Why? We'll get to that. So if you know how attention works and you know that how a model understands a sentence is by generating queries and keys for those particular queries. That's how something like a GPT understands or gains understanding of a language. So if we go back to the sentence, which is I am going to play football in the evening, um, how GPT would try to understand this is by creating a query. So let's say it creates a query for I and asks, where is the verb for I? So this is the query. The key for this particular query will be in the word play. So this would be the key, the answer to this question, or some, which is what? Which is four positions to the right. So by generating, so they're going to be thousands, and I'm not sure of the magnitude, but they're going to be a lot of keys and a lot of queries. So what we want is that the model's keys and queries should align such that the key for play directly corresponds with the query for the verb associated with I. And for this alignment to work effectively, we want it to be linear transformation. If the transformation of positional encoding due to a shift in position is linear, then the model can easily adjust keys and queries to reflect these small changes without losing the relationship between words and their positional context. So mathematically what this means is this, that PEX plus delta X is equals to PEX or dot product with transformation matrix, that is a linear transformation. So thus linear transformations are not just a convenience and we kind of need it. So now we have understood that we need it to be linear. Now we're going to skip to another concept of a rotation matrix. So if you know how rotation works in a 3D space, great. If not, I'll give you a high level overview. So to rotate a vector in 3D space, we need to multiply the cos theta and sin theta with this rotational matrix, which is cos phi minus sin phi. We have a sin phi and a cos phi. So here you see that if we have a cos element in our positional encoding matrix, we'll be able to translate that vector in 3D space very easily to answer our keys and queries, to answer our queries with keys, right? So if we replace each sign with a sine cos pair, so if we look at this particular graph, what if we add a cos instead of a sine, right? As the second dimension, or we just create, let's say we have n frequencies of sine curves, we just add n another frequencies of cos curves. So we'll have 2n, something like that. So what we're going to do is we're going to replace each sine with a sine cos pair. So what we're going to have is something like this. Right? And so on. So once we get this, we can do rotation. So let's look at this particular row to basically get to the final formula. So a positional when encoding of at x will look something like cos omega naught x Then we'll have another sine omega 1x, we'll have a cos omega 1x, and so on. And what omega over here is, if you look at omega, let's call the subscript k, what the authors have used is 10,000 to the power 2k upon d where d is the dimension. And this 10,000 is, we can call it a magic number, what the authors have used. How did they get this number? My theory is through experimentation. Again, I'm not sure, but this is what the authors have used. Right, so this setup not only maintains the unique encoding for each position, but also ensures that the encoding is distributed smoothly across a multidimensional space. And this multiple dimension distribution is akin to a vector rotating in space with a small change in angle. And by angle, we mean position. And what does this do? This results in a predictable and consistent change in the vector's orientation or encoding, if you want to call it. So there you have it. We've taken quite the journey through the mathematical landscapes of positional encoding, from simple numbers to normalized numbers to binary representations to a sine curve to multiple frequency sine curves, then to multiple frequency sine cos pairs. And we have seen how transformers harmonize the sequence of words using this elegant mathematics of sine and cosine waves. Thank you.